Okay, so we are recording. We're on lecture 27. This is our last lecture this week before Thanksgiving, and we'll pick this up on next Tuesday. And that's the day we have our homework due. Today, we're going to talk about minimum spanning trees, which changes a lot for us because we're moving over to weighted edges. Weighted edges are kind of going to break our data structure. So we've been getting away with this relatively simple adjacency graph. We'll review what that is, but we're going to need to move away from that. And we got a lot of territory to cover today. Unfortunately, I'll try to kind of keep the pacing good so we get a good recording on this. But essentially, we got a good amount of territory to cover to get to our important algorithm for today, which is minimum spanning trees. So we'll have a small lab for today that's due on Friday. I'll be pretty lax with this. Folks get it in before the next class. I'll grade it, but you got to kind of put some limits on it. So please do try to get that in before Tuesday next week. Then, of course, we have our strongly connected component problem from homework 7. And lab 26 should have everything you need, but also please do use the code that's available. It should save you some time. I don't want you guys to have to reinvent the wheel. Now, our quiz 7 on Tuesday will include this lecture. So it will include conceptual questions about our minimum spanning trees. I'll show you one of the questions or two of the questions today in our lectures so you'll know what we're talking about. It's not too hard. It just really tests your ability to think through the algorithm without having to write any code to find these things called minimum spanning trees. And there's also a Quizlet that will give you some samples you can test if you need a little bit of extra resources to kind of get you through this little section of the course. Now, just a little word of note. So homework 4 is still out there. It's something that a lot of people do drop if they get 7, or they just skip it if they get 7 good homework grades. So we still have to get homework 8 in. So if you do well on 7 and 8 and you're happy with all your other grades, then you can kind of skip 4. But 4 is kind of the emergency, pull the handle if you need to, recover a bit. It's got some really good stuff. And if you don't do it now and you're looking for just a warm-up project somewhere in your future, make a copy of these homework 4s. They're really good, open-ended problems that are fun to tackle. So that's kind of how they were designed, but thought I would just mention that to you one more time before we go too far. Now, because Canvas will drop your lowest homework grade, if 4 is a 0, that's the one that'll get dropped. So that's just how that works. So really, you can pick any 7 good grades out of your whole kind of semester's grades, and you'll be good to go for your homework assignment. Now, just a quick word. I'm not playing too heavy-handed on this, but one of the reasons we keep our data structures really low level is we're really trying to level the playing field for folks coming from different languages. So I know that Java and Python and C++ also have lots and lots and lots of libraries. So I'm going to try to keep us, continuing to use the the classes that we've developed for the lion's share of our development. I know it's easy and tempting to rewrite this stuff that we've been talking about using higher level libraries, but please try to reserve your use of those for kind of peripheral stuff that you're doing. So I don't think it happened this year, but in previous years we've had some folks just throw out all the code and write from scratch. So I'm going to try to keep working with arrays because that really is our fundamental data structure. And in theory, when you leave this class, you should understand how all these other libraries in Python and Java and C++ do what they do. So maps in C++ and Java are hash tables or binary search trees, for example. So that's a little bit of the reasoning for the methodology. So if I push back on anybody in terms of your submissions, hopefully you know where I'm coming from on that stuff. Okay, so now today our real goal is to talk about minimum spanning trees, but because of our wonderful holiday that we had a few weeks back, we missed this important topic called union find. So you're not going to really be graded on your understanding of union find, but it is an important part of one of our algorithms today. We can't get around it. So I'm going to show you the code for it. I know it's going to be a lot. I'll try to give you a real quick explanation of what it's all about, but we're going to try to kind of fly over the top of it quickly so that we can get to this more important topic of minimum spanning trees. So hopefully that will kind of become clear as we kind of go through the code here in just a little bit. So minimum spanning trees are about, finding the shortest amount of wire to connect up a neighborhood, right? If we were connecting with electricity, and we'll talk a little bit about how that works. So one way to think about it is that even though we might be able to visit all each other's houses through lots of different roads that connect our houses, we kind of need to get power to all of our houses. And that can be done by just creating a tree that flows from the power plant to all of our houses. We don't need a bunch of cycles and different lateral connections. We just need a tree. And that is often referred to as a minimum spanning tree. So we'll look at some examples of that. A couple key things to review. Remember that Kosaraju-Sharir's algorithm is the primary one that gets talked about when finding strongly connected components. And strongly connected components are, of course, the equivalent of connected components in directed graphs. So one of the key things we need to do to solve that problem is do this topological ordering. Okay, so we need to figure out the topological ordering in order to then go through and find the connected components in these directed graphs. So we essentially will reverse the edges and then create a post-order traversal or a topological ordering from the reverse graph, and then use that ordering from that reverse topological ordering to finish our depth first search. So I know there's a lot there, but those are the key aspects of it. It's sort of create a reverse graph, topological sort, and then one more time go through and try to visit everything with a depth first search and tag the components as you go. And if you do it that way, you miraculously get essentially the equivalent of, connected components, islands, but they have this added characteristic that they must be strongly connected. Now, there are a couple other algorithms out there for that. We won't cover them, but this is really one of the primary ones that we might follow. Now, we flew over the top of a union find class, but let me introduce it here since we skipped it because we're going to reference it briefly. So once again, a union find is a class that we create. So the instance of the union find class is sort of a giant constructor that solves a problem. And this is from a case of problems called dynamic connectivity. So imagine yourself, where somebody's constantly building roads in some city and you want to know if two houses are connected. So you check in February and they say, nope, you can't get from A to B. And then you come back after one new road is connected. You say, are they connected now? Nope, not yet. So the union find class is a special kind of algorithm or data structure that allows us to keep rechecking for connectivity between two vertices as edges are added. And so the way we kind of do that is by creating groups. So we create groups that we know are connected, and then we add things to those groups whenever there's an edge that connects us to that group. So the key takeaway here is it's all about finding connectivity in a changing situation. And we'll see that get applied today in our minimum spanning tree kind of application. So I won't take you through too much of this, but the key thing we end up asking after we build a union find data structure is, hey, is vertex A connected to vertex B? If they are, that means there's a path, or there was a path at one time between A and B. And so this is a crucial algorithm used often in determining whether there's a cycle in a graph. Okay, so if two things already are connected and I'm about ready to create another edge, that would for sure create a cycle. That's what we're going to kind of use this thing for in our MST algorithm today. Okay. So I know that's asking a lot of you. You won't be tested on that. I just wanted to give you some context in case it kind of comes up and you have some questions about it down the road. So here's the algorithm symbolically. Like if I say, hey, I want to unify 10 and 8, that's like saying, hey, I got a graph edge here between 10 and 8. So that would be creating an edge from 8 to 10. But the union find data structure is not an edge-based or adjacency-based data structure. It's completely different. It just says, hey, all of these vertices are somehow part of the same group with the 3. The 3 isn't at any central point. It's just the first vertex we added to this particular club, right? So all of these things are connected, and so are all these things. So essentially, it's like a tree structure where anything that can reach the top is in the same group with each other. So over here, 10 is all by itself, in one group by itself. These are all by themselves over here. So these would not be connected. They would be two separate groups or two separate islands, if you will, in this union find structure. So if I unified 10 and 8, then I could say, hey, get the group for 8, and that would be 3, get the group, and my process of adding that is essentially going to compress or clean up some of those links progressively and eventually put the 10 inside of there as well. So although we didn't cover it, the unify process is one that creates connections to this group and then cleans up any long chains to compress it and flatten it out. And what that does is it makes union find the top of the heap in terms of the fastest way to determine connectivity. This process keeps these trees very shallow, and we can answer the question very, very quickly whether or not 10 and 5 are connected, for example. Because if they both are connected to the same root, then they are in the same group. Okay? So that's the idea between unifying and then checking for connectivity. So basically, this strategy from the union find implementation means that unifying something is almost constant cost, which seems kind of hard to believe. Whether it's 1 or 1 million things, we can test whether or not things are connected very, very quickly. So that is a really crucial part of it. Once we have constructed the connectivity, we can test for connectivity, or once we have added something to the pile, we can test whether they're connected very, very, very quickly. Okay. So this allows us to do some really incredible numerical processing. So imagine you have a porous piece of rock and you want to know if water can flow through it, for example. Okay, so that's like checking whether every little bubble is connected to some other bubble or there's something in the way. That seems kind of crazy, but it actually is very doable, and we have some code that we can show if we get more time later on in the semester to talk about it. But it's a very, very fast algorithm for finding connectivity. That's the key takeaway from that particular approach. Okay. So now another thing we're going to start doing is I've written a server that is called GraphMe, and we're just going to use this for a very quick and dirty way of visualizing graphs that we're creating on the fly. So the URL here, you're welcome to play around with it. We're going to have it in some of our quiz questions if you're curious about it. But basically, it's my server on Amazon, and I have some command line parameters that allow us to express a wide range of possible graph types. So if you know a little bit about URLs, question mark is kind of like, hey, here's another argument, and then here's another argument, and here's another argument. So the ands connect together interesting things like undirected, weighted, and here's my graph, and here's the number of vertices, and the vertex A, vertex B, and then for us today, with this weighting, we'll have a weight as well. So here's what that looks like. An undirected, weighted graph. Okay, so edges go in both directions, and they have weights, 4 vertices, and the first vertex goes from 3 to 1 and has a weight of 11, okay? So that third number is always going to be the weight, okay, for us. So if you click into these, and I think I can just do that, you'll kind of get a sense of this. Again, as I said, it's kind of cheap and cheerful. So that is the graph. And if you look, you can kind of see in the URL, right? That's everything we need. So if I wanted to change the weight of 0, 1 to be, 20 instead of 10, I just change that to 20, hit return, and now we see our URL kind of updates itself, okay? So it's dynamically drawing the graph for us. It's always going to put it in a circle. So if instead of 4 vertices, I said, okay, I want 20 vertices, right, in my graph, now I've got 20 vertices, and you can kind of see the connectivity is all over here on the side, okay? So there's a lot of hidden features in there. This is just a tool I created for discussion, for interaction, and some quiz questions. So you'll see that coming up later in the lecture, and you'll see it on your quiz 7 coming up as well. So hopefully it's helpful. The E equals 5 means there are 5 edges, right? So there are 5 triples of numbers in there. And N equals 20. I wish I had called it V. That's the number of vertices. Total number of vertices is 20 there, okay? So unweighted, let me take our 20 back to 4. Actually, I can just go backwards, which is kind of nice, right? Go backwards in my history. So here, I could say, for example, I don't want it to be undirected. I want it to be directed. So I change the U to a D, and now I have arrows showing the directionality of those connections, okay? So it's a little hacky. You don't need to learn it. But when we run our practice problems, it's going to auto-generate a URL that you can copy and paste into a web browser to bring up a quick, visual of whatever graph we're talking about in our code, okay? So it's just my way of, being able to get a quick, basic way of showing that graph. So you're welcome to kind of play around with that. We'll use it, and, like I said, you'll see it in some quiz questions coming up. Okay, so let's get to our core topic for the day, which is spanning trees, and then a variation on that called a minimum spanning tree. So first off, what is a spanning tree? So a spanning tree in an undirected graph is some subset of edges that connects all the vertices. So if I had 3 edges and 3 vertices, a valid spanning tree for that network is going to have the number of vertices necessary to touch all the vertices. So you can see it's going to be 1 less than the number of vertices, right? A minimum span or a spanning tree is going to have 1 fewer edges than the total number of vertices, okay? And there are multiple spanning trees possible, obviously, right? We could do a couple different kinds of spanning trees. Now, this graph doesn't have any weights on the edges, so we're really just looking at an undirected graph without weights, but these would be valid spanning trees. So if I were to ask you on a quiz question, hey, make me a spanning tree for that, you would just pick one of these 3, okay? And you'd be in a good place, okay? But the key thing to remember is it's going to end up being n minus 1 or v minus 1 in terms of the number of vertices. That's how many edges we will have in our spanning tree, okay? No more and no less, okay? And the other thing to notice is our spanning trees do not have cycles. So we'll follow that rule as we kind of move in to the minimum spanning tree category. So here's our minimum spanning tree, and we can talk about minimums now because it's a weighted, undirected graph. So now we're starting to talk about having weights on our edges. These could represent distances between cities, or they could represent resistance in an electrical wire, or the cost of going from 1 to 2, or maybe a transaction between two places. So very, very wide applicability of kind of adding those weights to those edges, okay? So back to our spanning trees that we saw, if we add up the edge weights, we now kind of have a cost, if you will, for that particular spanning tree, which is going to be different than that cost, right? Which is going to be different than that cost. And so one of the common things we look for when we're talking about these weighted graphs is what is the minimum spanning tree, right? So which is the combination of n minus 1 or v minus 1 vertices, or edges rather, that are going to give us the smallest weight. And so if these were kind of the cost of driving from city to city, including mileage and mountains and stuff, minimizing that cost has a real world benefit, right? We want to figure out how to hook up these cities in a least cost way, maybe to, for electricity or something else, okay? So that problem comes up quite a bit, and that's called a minimum spanning tree. Now, in this case, and in many applications, we don't care about directionality for the edges. So very often when we talk about minimum spanning trees, it means it's going to be in an undirected graph. And that's just kind of how that is, okay? And there could be multiple minimum spanning trees as long as the total weight is equal and lower than any other weights that would be possible when adding those edges together. Okay? So those are just some of the basics on the minimum spanning tree, right? So it's going to be a given some set of vertices in an undirected graph where there's some weight or cost and no cycles, right? We want to find the minimum spanning tree, or MST. It's a subset of edges that have no cycles and touches every vertex at a minimum total cost, okay? And there could be a lot of spanning trees, and there may be multiple minimum spanning trees as well in a particular solution, okay? Now, if we were talking about directed graphs, so directed graphs do not really have minimum spanning trees. They have something called arborescence. So this is not usually something we tackle in an entry-level algorithms class. So we will not really be trying to solve the minimum spanning arborescence problem for directed graphs. We're really just talking about undirected graphs here for our course here, okay? So I know we'll be throwing around a lot of these terms, and they might kind of get away from you at times. So let's just do some manual practice. So if I gave you a weighted undirected graph here and I said, hey, find any spanning tree, well, you gotta just have to remember that as long as you don't create a cycle, you need n minus 1 edges. So what's n, or v? The number of vertices. So 2, 4, 6, 8, 10. So I need 9 edges to create a spanning tree. That may not be the minimum spanning tree, but you can just start anywhere and start visiting nodes and just try not to create a cycle, okay? So we could I'll see if I can do this without screwing up, right? I'm going to go here, and I'm going to go here and here. So that's 1, 2, 3, 4, 5, 6, 7, 8. Okay, so no cycles. I got 8 and I have 10, so I haven't really, I feel like I've missed something. Wait, 1, 2,
J, bottom right.
J. Okay, right. So oh, right, yeah. So that didn't work out very well, right? So I probably could have gone around this way, right? And then not done that one, and I would have a spanning tree. It might not be the minimum one, but at least it's a spanning tree and no cycles, okay? So that's kind of what we want. So, and here's a different one, right? So here's another one. It doesn't have to be a singular path. It just has to be kind of all connected in a tree-like structure. Okay. So we could find all sorts of, spanning trees inside of there. It's just going to be kind of n minus 1 or v minus 1 edges, depending on how we kind of treat that total number of vertices. Okay. So here are the weights all added up. Okay. So 9 out of the 10 vertices. Okay. We do it again, different way. We add those weights up. There's 9 out of 10 vertices. Okay. So we're getting down to 35. And you can, poke around a little bit and see, what it feels like to try to figure out if you found the lowest value. Okay. So usually there's always one more smaller, especially as the graph gets bigger. It's kind of hard to kind of feel total confidence. But here we found a 14, basically. Okay. So the trick is, how do I go about doing this in a way that I find at least one of the minimum spanning solutions? And how do I know when I've created a cycle? Because I'm not allowed to create cycles. So if adding an edge to the list of edges creates a cycle, well, then I have to skip that edge no matter what. Okay. So that's the real trick of this. And the solution, there are multiple solutions. They've been around for a while. But the key thing is, we kind of know it's linear with respect to the number of edges. Because if we had a list of edges, we're only going to look for the smallest weighted v-1 edges. So it's like, okay, maybe we need to sort our edges in order, ascending order of weight, and then just consider each edge. That would be maybe the first thing that we could do or think about doing. But I would then need to sort E edges. If E is the total number of edges in our graph, that means we got kind of best case n times log of E, or, however many edges times the log of that number of edges. That's our best case sorting algorithm performance, or our worst case sorting algorithm performance, let's just say, that we've looked at. So, okay, that's one of the costs of doing this if we take a let's sort all the edges approach. So just kind of keep that in mind as we go forward. So the applications for this are humongous. They are everywhere. Minimum spanning trees come up all the time in designing networks for code, TV, computers, roads. There are applications of it inside of other algorithms, as we'll see. There's something called the Steiner tree, and there's a famous traveling sales problem. This is kind of the Hamiltonian tour we touched on briefly. And there's a number of other ones that where we could kind of use this to estimate problems, including cluster analysis and a few other things. So applications are wide. All we really need for this thing, though, is a way of representing the tree and then a way of kind of going through edge by edge by edge. So there are a couple relatively famous different approaches. So we're going to look at Kruskal's, which utilizes the union find and a priority cube. So in the case of prims, it only needs the priority cube, but we're going to look at Kruskal's today. And remember that a priority queue is a pretty useful thing because it does not sort everything completely. It only gives us the next most important thing from the top of the priority queue, and it's faster than sorting. So there's a little hint as to why we might be using the priority queue. Okay. So let's look at how Kruskal's algorithm works at a high level. So let's call this V equals 8 for my number of vertices, 2, 4, 6, 8, okay, all with edges. So I would like to process all the edges in ascending order of weight. So find the smallest edge, and then you can either sort it or you can throw all the edges in a minimum priority queue, and that's cheaper than sorting. So if you remember our minimum priority queue, it's a binary heap. And so pulling something out of the top of it is actually a pretty low cost. We don't have to sort everything. We just need to get the top v-1 things. So if I have 1,000 edges, but only, well, this wouldn't be the case. Well, let's say I have 100 edges, but only 10 vertices, then I really only need the top 9 edges. So there's no point in sorting all of the edges if I really only need the smallest 9 edges in that case, right? So if we put them in minimum priority queue, we just pop the smallest one and then ask ourselves, is it going to create a cycle with the edges I've already found so far? Okay. And if it's not, then go ahead and add it to a collection of edges that we will consider to be our tree. And when we get to v-1 edges that we've collected, just stop, right? Because we know we've found our tree, because we know that's kind of a rule. If it's got v-1 edges, we know we're done. So let's sort of look at how we might do this. So let's find the smallest edge. Let's say we get it from our minimum priority queue from 0 to 7 has a 16 value. That's our smallest value here. Does that create a cycle? Well, no, because we don't have any other edges so far. So let's collect that. Okay, so we'll color our collected edges in blue. Okay, and then we'll take the next lowest one. Again, our minimum priority queue gives us this for a really low cost. So now we have 2, 3, 17. Nope, that doesn't create a cycle. Okay, so that Does it create a cycle? We're just using our big brains right now, not an algorithm, but it's like, I don't see a cycle there. 1,7, right? So 1,7 is a 19. We're still safe there. So we'll take that. So we'll just kind of keep going. 0,2. 0,2 is okay. Still no cycles, right? 5,7. 5,7's over here. So that's okay. Still progressing in an ascending order of weights. Then we get to the 1,3. So 1,3 is candidate because it's the next lowest weight, but that would create a cycle, right? We would end up with something like this. So we can't add that because it technically would no longer be a tree. So we're going to skip over that one and keep going. And we see the next problem with 1,5, right? 1,5 would also create a cycle here. So we don't want to take that edge, okay? So we'll just kind of keep rolling on here. 2,7, skip that one. So the ones in gray we've skipped because they would create a cycle. And then we sort of add the 4,5. And as soon as we get to V minus 1 edges, we know we're done. We should stop, okay? Now, how do we decide a tie between two equally weighted edges? We don't have any in this graph, but it really just depends on construction order. So with equally weighted edges, we might have multiple MST solutions, okay? And which one we get will depend on how we constructed the graph, what order our adjacency list is in. But we'd still get a valid answer, okay? So that is Kruskal's algorithm. Okay, so use a min priority queue, pop smallest, ask yourself, will it create a cycle? If it doesn't, add it to the list. So our min spanning tree is, of course, the blue ones here, all gathered up into one place. So we want to build that solution, right? But unfortunately, it's going to change our foundation in some non-trivial ways, okay? So we're going to look at kind of the rest of the day today. How do we go about doing that and sort of playing around a little bit with that code, okay? First one, as we mentioned, how do we find the smallest edges, right? We only need V minus 1 of them. What data structure would that we've studied would do that for us? The priority queue, okay? Really important example of why remembering what it does is so useful for a lot of situations. It's cheaper than a sort, right? Popping those things out of there is cheaper than a sort. And so the construction plus the pop is still cheaper than a full sort on, let's say, 1,000 edges as opposed to V minus 1 edges, okay? Okay, how do we avoid cycles? So how do we know whether a particular edge is going to create a cycle? We could do a depth first search of the graph every time we're adding an edge and then take that edge back, right? If we decide that that created a cycle, but that's a pretty expensive operation, right? A depth first search through a whole graph could end up being relatively expensive. And this is where the union find that we unfortunately had to skip over comes into its own unique features. It allows us to test connectivity in almost constant time, which is pretty darn cool. Okay? So here's how the union find kind of works. So imagine that we've got our graph, but in parallel, we're going to create these different groups, groups 0 through 7. And it's not a coincidence that they match the vertex numbers of our graph, okay? So two parallel data structures, okay? And so every time we find an edge, we're going to try, or every time we add an edge, we're going to join these two or unify the two vertices together in a group, okay? And if it turns out that they're already in the same group, then that would actually create a cycle. So let me show you our algorithm again. So 0,7, we're like, okay, we're going to unify 0,7. So now we group those two things together, and they really kind of form a tree over there. So now 0 and 7 are part of what we consider to be the same group. They have been unified, and therefore there must be some pathway that connects them together, okay? So remember, this is all happening in parallel to our graph structure down here. So as we continue, we'll say, okay, 2, 3, let's unify those two. So now they are connected, okay? And then we'll go ahead and get 1, 7, right? And connect those. But notice that by unifying 1 and 7, I've also kind of created a situation where I can very rapidly test whether 1 and 0 or 1 and 7 or 0 and 7 are connected. They're all part of the same membership of this group, okay? So union find doesn't really remember edges. It just remembers group membership. It's like, okay, these nodes are all together here. So we just sort of keep doing that. We keep doing that. When we finally get to a place where we potentially have a bad edge, we say, oh, I'm thinking about adding 1, 3 here, but wait a minute. Before I do, let's see if they're already connected. Oh, they're already connected. So if I were to add that edge to my MST list, that would be a cycle. So the fact that they're already connected before I try to unify them means that would be a cycle, okay? So the combination of these two data structures allows us to say, I'm about ready to add this edge, but would it create a problem? Yes, it would, right? Because they're already connected, right? They're already connected this way. So adding that edge would be a cycle. So we refuse to sort of add that to our list of MST edges. Okay. So we just kind of continue that. We keep checking against the union find data structure and ignoring, and only when it's safe to add do we do that. But we keep updating the connectivity as we go, okay? So at the end of the day, right, we are guaranteed to not have any cycles, and it's the union find that helps us kind of guard against that. Okay? So that's why we use it. It's very fast to do that connectivity check, but it does cost us a little memory to actually do that. So obviously, if I got 1,000,000 vertices, I'm going to have 2 copies of 1,000,000 vertices out there, one for the union find and one for the graph itself. Okay. Now, because we skipped over the union find, we're going to wave our hands at that a little bit, but just keep in mind, it's there to help us avoid from finding cycles. And that's a pretty standard way of using the union find, okay? So if you ever run into it in your travels, you'll kind of know. So we'll utilize that data structure, unify as we go, and avoid adding things to the MST, right? To avoid doing the cycle, creating a cycle. Okay? So there will be one remaining group that represents the minimum spanning tree. So let's look at a interactive version of this. Let's jump on over to visualalgo.net. Okay, and I really like this particular one because I do think it actually helps a lot. So always worth kind of scanning these. It pretty much mirrors what we're talking about in class. But let's say I need a minimum spanning tree here, and I will use Kruskal's algorithm. And so you should see it checking lowest edge weight to highest. So it's using the priority queue to find those things and the union find to ensure that there's no cycles being created. So the orange edges are going to be the edges that will be in our minimum spanning tree. Okay. And we should, I'm guessing, yeah, we'll miss those fat 13 things there at the end. Okay. So you can do this, on any of the example graphs. Let me just take one more over here. And you might also find it interesting to do the prims, but we're not going to dig into that for purposes of time. But let's see if we've got a large graph here. So there's a pretty big graph. Let's go to Kruskal's. We'll speed that thing way up, okay? And just see how quickly it crunches through that thing. Obviously, if you're running this code in real time, C++, it's going to go pretty darn fast. Okay. Now, while this is cooking, I'll let you know that out of curiosity, I heard that we could get the entire graph for a fruit fly's brain with weighted edges that are directed that represent the connectivity in an actual fly's brain between neurons. And I found it. And so I've been processing this thing to put it in the format that we use in class, and it's got about 500,000 connections in it. It's a brain, right? And these things are called connectomics. And all of these algorithms can be run on these connectomics or these brain maps. So, and they are working on a human brain map, right? So once that thing is done, graph algorithm analysis can find some pretty fascinating things, right? Which is pretty cool. So there's our minimum spanning tree. That's the minimum sort of cost to connect up all of the vertices, or in the case of a brain, right, all of the individual neurons inside of the brain, which is an interesting property to be able to compute. Okay. And that goes way, way, way faster in C++, of course. So let's take a look at what I would like you to understand. So if I gave you a quiz question, I said, I would like you to go ahead and find the minimum spanning tree. So it's really just about remembering you do not want to create a cycle, and you need to do this in order of smallest to largest edges. So let's jump over here and look at this in web page. So this is an iframe for those of you who are curious that's hosting that web page we just looked at. And it has a mode where it allows us to sort of select the edges. So let's just work through a Kruskal's algorithm here. So I'm going to start with the smallest edge weight I can find. That's a 2. And you'll see it's going to tell us it goes from 3 to 4 at a weight of 2. Okay. It keeps track of my sum of weights, right? So, oops. And then I will kind of just keep working up. There's a 2, right? There's a 3. Okay. It's tempting to grab this 3 over here, but that would create a cycle. Okay. So that would be where you would kind of go, in a bad direction on this quiz question. So we don't want to create any cycles. So what's the next bigger thing? Obviously, we can go to one of the 8s. Is that a cycle? Nope. And if you scroll down and you see, okay, the correct answer is a total weight of 15, that's going to be your answer. So in your quiz, you're just going to copy paste this right there and paste it in for your quiz answer. Okay. So trying to keep things as simple as possible for these potentially more complicated things where you might have a lot of typos. So you can kind of interactively find your way through these graphs. It's going to give you a little bit of help so you can kind of see what's going on. And there are other features. We'll talk about what cuts are here in the next couple of lectures. But this kind of tool has some nice things built into it. Okay. So let's do one more. So the other one that we have here is this one. So let's try to find a minimum spanning tree for this one interactively. So, and these are, by the way, these are just our practice problems in Canvas. So if you want to just jump into Canvas, practice problems for today's lecture, I'll show you where they are here in just a second, but they're easy to find. So lowest weight to biggest, don't create any cycles. So 4, 4, 6, wait, let's leave that 6 off until we get the 5s, right? Okay, there's our 5 and 6. So 19 looks like we got it. We copy paste those into our answer and everybody's happy. Okay. So you will see these in quiz 7, which is due on Tuesday. That's why I wanted to make sure you saw a picture of that. If you can kind of do those quiz questions, you're kind of walking away with the most important understanding of how these things work. And this again is for Kruskal's algorithm. There are other actual ways to actually do this without Kruskal's, but that's just the one that we're studying today. Okay. So let's talk about data structure because we have to evolve. So this is our undirected graph with no weights. So the nodes here have the vertex ID of what's connected to vertex 0. So they're outgoing, right? So they're the outgoing adjacencies, 9 and 13, for example. So at first thought, you might think, ooh, maybe I can cheat. This is a linked list. Maybe I could just put the weight here in vertex 9. But if anything else was connected to 9, that wasn't an 8, I'm trying to see if there's a 9 over here anywhere. 13 is probably a good example. If I put a weight in the 13 for the edge weight from 9 to 13, somebody else that's going from 8 or from 7 to 13 is going to have a different weight, right? So this data structure just doesn't work. There's no real way to make that dog hunt, as they say. So we have to find a way to change our data structure so it is more edge-based than adjacency-based. Okay. So even with our directed graph, right, directed graph with weights or undirected graph with weights, both of these present a problem for us. We need a place to store the weight. And it's a fun problem because you can design a couple solutions for this. Okay. So we're going to look at one evolution of our data structure. And what we're going to do is we're going to create, instead of a node, we're going to create an edge class. Then we're going to create a edge-weighted graph. So it's not going to just be a graph, but a special edge-weighted graph class. And then finally, we'll be able to apply our Kruskal's MST algorithm using those two new classes. So we're kind of introducing three new classes here that we're going to plow through somehow in the next half an hour. Okay. So we're going to have, so rather than having just a node, we're going to have this edge, and it's going to have two vertex values in it. And you can think of it as the from and the to, and a weight. And we need to hook these things up together for all of the edges emanating from a particular vertex. We're going to call that next adjacency. So if I'm vertex 0 and there are three edges flowing out of me, then I'm going to have a next edge link. So it's going to be a linked list of edges using next ADG inside of that edge data structure there. So that's going to allow me to have edges linked together for a particular vertex. Okay. Now for undirected graphs, we still are going to need to duplicate things like we were duplicating with the nodes. So we're going to have some duplicate data there, but it's manageable. Okay. So we're going to have edges that flow from 0 to 1, right? And then edges that flow from 1 to 0. And they're not going to be shared. We're not going to use the instances idea of this, okay? So all edges is another thing we need to do, because if you think about it, we need to have a one grand list of all edges with no duplicates so that we can run our Kruskal's algorithm. So we need kind of two links or two linked lists that flow through these edges in different ways. One is every edge in the graph, and one linked list is the edges in a particular adjacency for a particular vertex. So we're going to work with two simultaneous linked lists in here. Okay, but first let's zoom in on our edge class, because this is kind of cool. So we're going to call them A and B for our from and to vertex. But we kind of want our vertices to be potentially, bidirectional. So we're going to start by just calling them A and B, and we'll have a weight. And here are two sort of linked lists that this edge could be a part of. It could be a part of the grand global linked list for all edges in a graph, but it could also be part of an adjacency linked list. So it's going to be part of two separate linked lists running through it potentially at any time. So our constructor is just going to initialize the key elements that we care about in the edge. And then we have some interesting functions. This is a neat trick, or some interesting methods. If I say, hey, give me one of the vertices of this edge, we're going to call that either. We don't care about whether it's from or to, because it's just going to be in an undirected graph. So give me one of the vertices. And then if I want the other vertice, I will tell you, I'll give you the A back and say, give me the opposite of the A. So other V means if A is equal to V, give the person back a B, otherwise give it an A. This is a cool little trick that will serve us well to make this edge work in a lot of different ways. It works for flow graphs, minimum spanning tree graphs, all sorts of things. So we're going to kind of use that, as we continue using the structure. Then we have some getters for getting the weight, and a print me method, which is going to save us from writing some code when we need to do some debugging. Okay, so this is a nice little edge class, and we could add some other features to it, but for now, that's going to get us pretty far. Okay, this is the trickiest part of it. We have to imagine that this edge could be like having two pieces of thread running through it. One connects like popcorn on a tree, right? For the holidays, we could have one collection of thread running through it for all edges and a different thread running through it to collect up adjacencies. And we'll look at that picture right now. So we still have our good old adjacency array. So what are the edges for vertex 0? So if I have an undirected MST, right, over here, we have 0, 1, and the weight, and a next adjacency pointer, and we have to duplicate or clone that just like we did for our adjacency graph, okay? 0, 1, 1, 0, okay? But at least we're talking edges now, not individual vertices, okay? So as we add more of these things, we add on the next adjacency, right? And then we go 3 to 0. So we're still going to have a linked list. It's just that it's a linked list of edges, right? So it's an E star data type in each one of these pointer fields right here, okay? Add another one, add its duplicate in the other direction, and there we go. So those are our ADJ or next ADJ pointers, but as I'm building these, I need to seam together a unique collection of all of the green ones, okay? So that when we run our Kruskal's algorithm, I can very quickly move through all unique copies of that edge. So I don't want to sort of link them all together, just the green ones, because otherwise I'd have two of the same edge in my list of all unique edges, okay? So next ADJ takes us to the adjacencies. Next all takes us through a global list or global list for the whole graph, okay, of just the green ones. Okay? So a little bit of extra bookkeeping, but we can kind of make it work, okay? Now, some of you might be thinking, couldn't we have an instance of this over here, 0, 1 and 0, 1? Couldn't it be the same object? And the problem is no, because the next ADJ is going to be unique for each of these vertices over here. So in this particular case, we really do need to make a copy of that. Otherwise, we kind of muck up the adjacency list. So that's our new data structure. We're going to live with that for a little while, okay? So here's us kind of thinking about this, a different graph. I don't know why, I forget why. Oh yeah, just showing us a different graph, right? So here's our global list, right? Going through our unique ones. Right, this is directed, right? So you see it's a lot simpler than the other one, right? This is directed, and the other one is undirected. I wish there was a fast jump back and forth there, right? There's our undirected graph, a lot more dense than our directed graph, okay? Looks the same, but we have arrows on this one, right? Okay. So those things haven't really changed any from what we saw last time, okay? All right, so let's look at the edge class. So if I want to create an edge pointer E, I'm going to say edge star E equals new edge 1, 2, 32. So I'm calling the constructor, getting a pointer back from new and holding on to that pointer, okay? So we can think of this as the from and the to, right? The from and the to, but in an undirected graph, it really doesn't matter too much, the weight of 32. So I can say E arrow get weight, calling my getter using the pointer in C++, or I could say, hey, give me one of the vertices, right? We'll get the number 1 vertex there. And then the other from 1 on the same edge would, of course, be 2. So that's the from and the to. And you could call it from and to, but then it implies some directionality, which isn't always something we need. So we're just going to kind of make it generic for now, okay? And if we want to get the other of the 2 for some reason, then it's really easy to do that. We just say, hey, I got the 2, give me the opposite of the 2, because I need to go get that one, okay? And then the either of the other or the other of the either does what you might think it would do. Okay? So just kind of a new idea. We're going to kind of use that in most of our algorithms going forward. So now we have to build a new graph. Okay, so it's a new graph class that handles weighted edges. Okay, so now we're kind of stepping up to some serious number crunching here. So we're going to have an array of adjacencies. Remember, that's a double pointer because we're going to dynamically allocate an array, right? So it's our stacked ADJ array there, right? And then just a single pointer to the head of all edges. So we want to manage that, and the rest of these things should look a little bit familiar. So we construct it, we create our all edges is, our linked list of all edges. It starts out null. Our 80J is an array of edge pointers, right? So each one of these is our adjacency list, right? Adjacency list, adjacency list. And the other stuff we've kind of seen before, okay? Down here, notice when we add an edge, we're passing in a pointer to an edge, okay? When we add an adjacency, we're passing in a pointer to an edge. So we got to allocate the edge outside of the call, and then we pass in the pointer and the VID that it's the adjacency, that's part of its adjacency, okay? And when we get 80J edges, we're going to get a linked list of all of the edges for that particular VID, right? So this, let's say, would be 5, right? Position 5. So if I say get adjacency edges 5, it's going to get me the big linked list of all those edges over there. Okay? So that is kind of our graph class. So let's just look at how we use it real quick. So we're going to create a simple graph, edge-weighted graph G3. So it's going to have 3 vertices. That's what we have. Then we're going to say add an edge, new edge 0, 1, 22. Okay. So what is new doing? New is returning a pointer that is going into the add edge method. Okay. So this passes a pointer to this method. What is the pointer pointing to? This new edge on the heap, right? So now this is going to be how we're going to go ahead and build our graph. Okay? So we're going to create the edge and immediately pass its pointer into that particular method, okay? And we can get our vertex count, and we can get a pointer to all the edges at any one time. Hey, give me a pointer to those edges. Not a copy, so we're really kind of getting a live pointer to the adjacency or to all the edges in that particular graph. Okay? So we wouldn't want to take this and destroy the edges out from under that graph, for example. Okay, so we could say while e is not equal to no pointer, e arrow print me, that prints the edge, and then e equals e next all. This is how we would move through a linked list of all of those edges. Okay. Okay, so this is kind of the global list inside of the whole graph. Okay. So let's see if we can finish the implementation of the edge-weighted graph class, okay? Now, I think I can code and talk at the same time on this one. Let's see if I can, but let me just show you some solutions ahead of time, right? So adding edge shouldn't be too much of a change, right? So we're given a pointer to an edge, and we're going to push it in at the head. So we're going to say E next all, this edge is going to point to the head pointer. So this is a classic pushing something in at the head of a linked list. So we're going to take this, hook it up to the old linked list, then take the all edges and point it at this one, okay? So now we've shoved that edge in at the beginning of all of the edges. So we've handled the global list here, okay? Right, that's part of the larger class that owns this. And then we're going to do the either other thing. So we pull out the VA, VB, and W, and we add an extra, we add the adjacency, VA and E. And if it's not directed, we add VB and a copy of that edge, okay? We have to actually make a copy. Otherwise, we screw up our data structure. That is a really subtle point right there. Okay? That copy. Okay? That's that blue copy we saw on the previous page. So you might think, why does this matter? It's not the code that I want you to see, but that, the algorithm is relatively straightforward, but making it work in code takes a little bit of extra, sauce, right? So there's our add edge, okay? So you can kind of probably find that pretty quickly in the search code there, okay? And of course, this is where the duplication happens, right? That's our kind of wasted extra memory, but it kind of serves us well, okay? And so basically we need to create this weighted graph so that we can kind of move on to our minimum spanning tree. So now we have our edge weighted graph. We have our new edge. We can access the edges in sequence. And so we can apply a number of different algorithms now with this new enhanced edge graph, okay, edge weighted graph. So, and we'll do pathfinding with them as well very soon. But let's look at our final step, which is the Kruskal class. So again, we got some simple graph and we want to create an edge weighted graph of it, right? So we're going to add our edges to build up our graph, maybe through a for loop, maybe through a file, or what we did for homework 7 or what we're doing for homework 7. And then we want to do is create an instance of the Kruskal class using an address of that graph structure, okay? So G here, since we created it without a new, we're just going to pass in the address of that. And now our constructor for Kruskal should create something like this. It's going to analyze the graph and create for us an array, just an array, with n-1 pointers to edges, okay? So it is going to be an array with a whole bunch of pointers to individual edges that it's borrowed from this graph, right? Whatever that's not what I wanted to do. Whatever the minimum spanning tree would be, it would be this edge and this edge. So this would be really this edge here and this edge here. So we're stealing pointers from the graph and hooking them up in an array that's part of this brand new MST class. And once the constructor is done, we have our list of minimum spanning tree edges. And Kruskal's algorithm is basically going to run inside of our constructor, okay? And it should list off those edges for us, okay? 1, 2, and 01, 22, okay? So that's where we're going with this final class. So here is kind of a high level view of it. Needs to keep a pointer to an array of pointers. So it's a double pointer in C++, slightly tricky business. It's got to keep the sum of all weights just so we can ask what is the minimum spanning weight. And then we have this, to be filled out constructor here. I give you the graph, you give me back, calculated sum and linked list, okay? Now, in order to do this with a priority queue in C++, we're going to break my golden rule a little bit. We're going to use the C++ priority queue for sanity's sake. And in order to get that thing to work, we have to create a class that knows how to compare our edge weights. So in C++, we do that by overloading the comparison operator, okay? So we'll say, okay, or the comparison operator, and we'll basically say, hey, if this one's weight is greater than this one, return true, okay? Otherwise, return false, okay? It's basically going to allow us to do something like this. If edge 1210 is greater than edge 12420, okay? It's definitely some tricky stuff. We go over it in Comp 235. Again, that's this spring online if you're interested. But this is going to allow our class to use the off-the-shelf priority queue from C++. Okay, this is complicated, I know, but we're saying, hey, I'm going to have a priority queue of edge pointers, and we're going to be comparing these types of things that are going to be in an internal vector. We're going to call that PQ, okay? So if you think about our Kruskal's algorithm, we need a priority queue to put edges in, okay? We're going to create our union find using our union find data structure, okay? And then we're going to process that linked list there. We're going to push all of the edges into PQ, and it's going to automatically put them in that heap structure so that the smallest thing will go up on top. And this is what's ensuring that the smallest thing goes up on top, okay? So we're holding on to pointers to edges, sorting them be this special class here. And that's going to be what happens in that area. We're not really sorting. We're putting them in a priority queue. So here we can say, while that queue is not empty, and while we have not collected too many edges, right? So graph vertex count -1, that's our goal, collect that many vertices. We're going to use our union find in the middle here to decide if it's safe to add that edge. So that's going to be part of that unify process. So we'll get the smallest edge, we'll get or the VID or the vertex IDs and check it against the union find. And when we're done, we should just be able to go through the MST edges array, right? This dynamically allocated array up here will have all of our vertices in sorted order, okay? So that's a lot. Let's take a look at the solution for that. I'm not going to drag you through all the coding, but it is instrumental in kind of understanding it if you get the time to look at it. Just one more time before we do that, why not sort? Why not just sort everything and just do away with this messy minimum priority queue? So in other words, right here, we could just apply a sorting algorithm to sort all of the edges into some array, and that would be done. And that would work, but it would be at best n log n or v log v, right? That's how many kinds of things we would have to sort in order to make that thing work, okay? So if I had only 7 vertices and 7 edges, that's not a very expensive sort. But imagine if I had every possible dense connectivity for those 7 vertices. Now that sorting algorithm, when sorting edges, ends up being more expensive. So for dense graphs, the priority queue is really going to be a much, much better solution, right? Rather than having a log base 2 kind of situation, we're going to have something that is going to be, or rather than having a log base 2 of 6, we're going to have a log base 2 of e times e here, which is going to be much, much worse, okay? So priority queue is really, the answer there, okay? So let me just sort of highlight the code for this again, rather than dragging you through all of the changes, because I'm bound to create some problems. But let's take a look at our constructor. So here's our constructor. We create a union find. For each edge in the all edges linked list, as long as we haven't hit the end of that linked list, move to the next edge. Push that pointer into the priority queue, okay? So we're preloading our priority queue with edge pointers. And the magic of this is going to float the smallest edge to the top based on this piece of code we wrote here. Okay. Now we go through and take them out one by one. Okay. And we say, okay, go get the edge, pop it off the top. Okay. Get the vertex ID of the either and the other. And if they are not connected, then connect them in the union find and add that edge, right? The smallest edge that we got to the particular count location of our array. So we're just collecting up an array full of these sort of v-1 edges. And then increment our counter. So the next time we go around, we put it in the next slot and the next slot and the next slot. So we're collecting pointers in this data structure right here as we pop them out, as long as they don't create a cycle, okay? And then we pop that thing off the queue and we go around and do it again. So that is Kruskal's right there. And the final thing we do is just say, oh, okay, here's your edge list, right? I'll just go through and print them out for you, okay? MST edges of I is a pointer to the print me method, and off we go. I think those are the big things, okay? So, here's the kind of zooming in on that part there, right? Just so we can kind of all see it close up, right? That's us loading up the min priority queue. So I'm just zooming up on this code we just looked at here. That's the min priority queue. That's our kind of sort. Here's our kind of wild part zoomed up there. Again, if they're not connected, go ahead and connect them and add it to my list. Otherwise, do nothing, right? Don't add the edge. Okay, pop and continue. And then the last one zoomed up here, right? There's just us printing out that dynamic list of edges, okay? So a lot of code, but let's take a look at the performance. So, and we've really only looked at Kruskal's here. So it's interesting in time, you may come back and look at prims and some of these other ones. But basically, we have space cost of E because we're basically storing an edge representation of our graph now, okay? So yeah, we still need our adjacency array, but it's going to be E for space. And then the time to perform this is going to be the cost essentially related to the priority cube. So we're inserting E edges and then popping V minus 1 edges. And so the popping is going to be proportional to the logarithm of E in this case. Why logarithm? Because remember that the priority queue is a binary heap very often, right? So we get a log kind of behavior from the cost of popping that thing out. Okay? So the good news is it's not quadratic, right? It's not linear, but it's linearithmic, and that's pretty good. Most of the good algorithms we find are either linear or linearithmic or constant, right? In the case of a hash table, right? It's a constant extraction. But here, Kruskal's actually solves this pretty important problem in linearithmic time, which is pretty good, okay? So nobody's been able to really figure out how to do it in linear time. There's an approximate linear time, but in terms of edges, but it's much more complicated. Okay? So there's still people solving these problems, right? Coming up with, faster solutions. Okay. So now, again, the takeaway for us on minimum spanning trees is not so much about the code, but just understanding the algorithm. So if you need to kind of take a look at these minimum spanning trees, and again, the Kruskal algorithm is the one we're focusing on. That's all we're really after. Okay. For our lab today, we're just going to try to apply a little miniature story problem. So let's work through the story problem together. And all you really have to do is wire up the main section and everything should work for you. But this is how these stories are usually done, right? So there's a town with some roads and there are 20 homes, right? And 40 vertices potentially connecting those, or 40 edges connecting those homes. So we want to find the minimum spanning tree so that some company can hook up power to all the homes, right? So all the homes need to be reached. They don't necessarily all have to be connected to each other. They just have to be connected to a tree that comes from the power plant. So we're going to say PG&E stands for pretty good electric. I didn't want to get sued. So PG&E has said that it's going to cost them $103 or 103 whatever units of cable. So you need to figure out what the minimum spanning tree is and just figure out whether that bid is a reasonable bid or not. Okay, so you can do it in any silly way you want, but is 103 above, below, or equal to the minimum spanning tree for this particular graph? So it's a pretty classic just application of it. Now notice that when you run this thing, there's going to be a GraphMe link in the output. So don't kill yourself by trying to figure out, what this graph looks like. Just copy and paste that particular output into the URL, and you'll get to see a picture of the graph. So it'll help you kind of verify your answer there. Okay. And so provide your answer in a submission comment, and of course submit your code as well, so I can just see that you got the code working okay. Okay. So we've got a V equals 20 and an E equals 40, and you're just going to have to create these things from the code. So let's just quick scan the code real quick so you can kind of see what we're looking for. Okay. Sorry about that. Just burn everybody's eyes out. So the full story is here. The steps are here to guide you. There's really only 3 steps there. All of the code is there for you. You didn't find edge class, edge weighted graph, Kruskal class. Okay. Here's your data, right? So just like you did for your other homework assignments, you're going to create a graph, add the edges using the new edge weighted graph, and then call Kruskals and just ask it what the sum is. So there's really only about maybe 10, 15 lines of code in that main section that you got to write. Okay. Okay, so again, due on Friday technically, but I'm going to be pretty lax since I know that we'll all be kind of doing things for the holiday, but please try to get it in by next Tuesday. I really appreciate that. That'll help me stay on top of grading. Okay. Questions before we adjourn then?
I just still want to mention that was protocol of this Friday, so no in-person meeting or Zoom meeting.
Okay. All right. Thanks, everybody. Have a safe and relaxing break. If I don't see you, I'll see you next Tuesday. I'll be checking my email. If you got questions, you get stuck. Thanks. Have a good holiday.